Let's quickly walk through okay. Kinetics for a rigid body as opposed to a point. We call it a review. We'll have mostly two dimensions. This is our two-dimensional body. And this is center of mass. This is fixed point O. So we developed, if you recall, the following equations. We had some of the okay, this is X and Y. Some of the forces in the X direction equals to mass of the body times acceleration in X direction of the center of mass. Let's write it down. Acceleration of center of mass in the X direction. Sum of the forces in the Y direction equals to mass times acceleration of center of mass in the Y direction. And we had some of the moments about O equals to IO alpha. Alpha equals to d omega over dt. S sub O is mass moment of inertia. About O. O is fixed point. That's version 1. You can use this if you know for sure that there is a fixed point. You can sort of make this one more geometrical by showing like this. This is the resultant force. Okay. And this is the acceleration. And it's equal to mass times acceleration of center of mass. So that's the equivalence that is given by these two equations. We had some examples of figuring out the mass moment of inertia, right? We did for a disk, for a rod, right? Okay. Just a reminder that you have, I think, Appendix D in your book has mass moments of inertia and CGs. Let me double check. It used to be there, and centroids. Let me double check in your book. I'm pretty sure it used to be there in previous editions, but we all know that they come up with new editions, so to keep us in our toes. Or is this now in a different appendix? I think it's in Appendix B. You guys ever look in your textbook? In the sober state? Yeah, I can never find this table. The problems are here, but the tables of section of properties. Look at the table of contents, whether it's going to be listing there. Page, yep, table D4, right, so page 321. Yeah, it's Appendix D. I was right. Strange enough, they didn't change. What else do we know about this stuff? Parallel access theorem, right? I about point A equals to I about center of mass plus M D squared. Let's show point A somewhere here and show this as a D. Now, the version 2 of the equations is about center of mass, as that's usually the one of choice, version 2. I'll write it a little bit abbreviated form. We have the F equals to M A center of mass. That's the same, but M about center of mass equals to about center of mass times alpha. This is 2 equations, this is 1. So we have 3 equations. Usually the book, the textbook, our textbook, offers some artificially constructed problems which require to do it in version 3. Version 3 addresses only the moment equation. So what it does, it looks at your statics background and say we want to have what's going to be so let's draw another picture so you'll see it there. Center of mass. And the moment equation looks like this. We have this is the moment about center of mass, and it's equal to the I about center of mass times alpha. And we want to find something about point A, and we also have a center of mass, that's the resulting force, F, that's equals to MA center of mass. You know what? Scroll it back. Let me draw it in another direction. That way it's going to be more easier to do. That's going to be it. Sorry. It's going to be F equals to M of A center of mass. So if you want in statics to find the moment about point A, right, knowing the moment about, for example, this point, we take the moment about this point plus the force, the resulting force, times the moment distance, right? So they use this thing to apply here. So the moment about A equals to moment about center of mass, which is I center of mass alpha, plus O minus F times D. And the F is MA, sorry, MA center of mass. This one times D, that's scalar, right? Okay, so, and that's going to be plus if, like this, counterclockwise, minus if clockwise. So that's version 3. The translation equations are the same. Last time we did the example with, remember the book splits it into 3 topics. One is just the translational, the other one just the rotational, the third one altogether. Okay. We did the examples on the first one, right? And so we'll do with the second one, and then we'll get to the third one, right? Okay, let's have an example. Meters. That's 24 kilograms. Yeah, we talked about vertical plane. This is constant moment. A constant moment applied counterclockwise acts on the L-shaped rod, ABC, which rotates freely in the vertical plane about the pin A. Determine the angular acceleration of the rod when it is in the position shown. We'll go top-down approach. We'll start with the most fundamental equation that will describe it. In this case, we have a fixed point. So sum of the moments about A equals to I about A times alpha. So now we have to sweat the details, right? Let's do the left side first. Three-body diagram. The horizontal piece is 20 kilograms. Okay. Sum of the moments about A equals to. It's going to go clockwise, right? It's going to be minus 20 times G times the moment arm. The moment arm is 1 meter over 2. Then G. We'll put the value of the G later. Make sense so far? Okay. Sorry. In this case, it doesn't really matter. We can use the same equation for a system of bodies. Even if they are pinned together, we'll still do that. The only difference would be that if it was pinned together, each of them would have its own angular acceleration. But since in this problem they asked for one, that means there is another. I about A equals 2. Let's call this object 1 and this object 2. It's going to be I about A1 plus I about A2. So for a rod, the moment about the center of mass is 1/12. So it's going to be M1 L1 squared over 12 plus M1 D1 squared. D1 is this distance. Plus M2 L2 squared over 12 plus M2 times D2, and D2 will be this piece, D2 squared. Bless you. So the M1 is 24 kilograms, 24. And we have L1, and that's 1.2 meters, 1.2 squared over 12, plus the D1 will be 1.2 over 2 squared. So M2, it will be 20 kilograms. And we have L2 squared over 2. It's going to be 1.0 squared over 2. Plus the D squared, which we'll use Pythagorean theorem to find it. And there's going to be 1.0 over 2 squared plus the vertical thing is 1.2 squared. I'll bring these things a little bit together. It's going to be 1.2 squared over, that's over 4, that's over 12, that's going over 3, plus this one 20. And that one will have to go directly. That's going to be 2.19. $55.32 mass is in kilograms, and that's going to be meters squared. Of course, where I didn't do right was right here, because this will be only portion. That's the gravity portion. So we need to plus the 180. Plus 180 is going to be minus 98.1 plus 180, and there's going to be 81.9. So we'll have the 81.9 equals to 55.32 times alpha. Alpha equals to 1.48 radian per second squared. Sir,
Where is the 180?
it was given. C is given the counterclockwise. Okay. Yes, sir. Say it again. I missed the 180. I should have written it to beginning. Okay, that was pretty straightforward. Now we'll do one more example. This is a bit more involved. Bless you. Okay. Mass of the bar is 1.8 kilograms. It rotates in the vertical plane about the pin at O. When the bar is in position shown, the angular velocity is 4 radian per second. Clockwise. Find alpha of the bar and the pin reactions. Let's label them somehow. So that's going to be OY and OX. So let's sort of hypothesize. Let's bullshit for a couple of minutes. Sometimes bullshit really brings out the best of us, right? If you want to judge a person, watch when he bullshits, right? That's if he talks intelligently, then everybody talks the same way. But person bullshit, then you can see the personality, right? And the features. Never mind. All right. For the alpha bar, that we can do pretty straight, at least the idea is straightforward. We'll write down moment about O equals to I about O times L. So we'll have to sweat out the detail more of I about O, but other than that, it's okay, right? Okay. And in the force, we'll include the force of gravity. There is nothing else here. Let's mark the gravity so we won't be mistaken, right? Okay. That's one thing, right? Okay. Now, where do we dig out the pin reactions? The pin reactions have no moment about O, right? So the only way we can do that if we go to the translational equation. Force equals to mass times acceleration in the center of mass, right? Now, acceleration center of mass, for that one, we will need to utilize your favorite stuff of acceleration analysis, right? Okay, I just started there, which is once we have acceleration and we have angular velocity, which is given, right? Then we can go from O, which has none of those, to the center of mass, which will have acceleration, linear acceleration of center of mass. And we'll write down the translation equation, and there we have it, right? So that's with a lot of hand waving or finger waving or finger showing, right? Okay, that's the idea. All right. Shall we go? Well, let's do that. That's roughly the outline of what we're going to do. Let's mark this one A and this is B, so we'll know what we're working. So the moments about O equals to I, equal to I about O times L. Whenever we do this kind of thing, don't ever neglect to show the free body diagram, right? Because if you do it without showing free body diagram, you'll be downgraded to accounting major, right? You don't want that to happen. Right? So this is our object. That's the point O. We have this one is mg. And we have these two are the reaction OY and OX. So, and the angle is given as 40 degrees, right? Is it? Yeah, I think I plan to do, yeah, that's 40 degrees. So this distance was 0.6, right? And the whole thing is 0.6 plus 1.4 is 1 meter. That means the distance to the center of mass is 1 meter, right? Okay. The whole thing is 2 meters, right? So therefore, this distance here that we really need for some of the moments is a 1 minus 0.6 is going to be 0.4 meters. So some of the moments about O equals to mg, and there's going to be 1.8 kilogram times g times 9.81 times this distance of 0.4, and we want the horizontal projection, which means we go sine of 40. You with me on that? Sine, not cosine, right? Now, this is going to be minus because it's clockwise. And that's going to be 4.54 Newton meter with a minus. I about O equals to I about center of mass. Let's say this is center of mass. About center of mass plus m d squared. About center of mass is 1/12 of mass, which is 1.8. Yes. Yeah, about 0.8. And the distance and the length of the bar is 2.0 squared, and plus the 1.8. And distance is 0.4 squared. Going to be 0.888 kilogram meter squared. So we'll have minus 4.54 equals to 0.888 times alpha. Alpha equals to 5.11 with a minus radian per second squared. Part B. You guys agree with me on your calculators? Part B. Sum of the forces in the x direction equals to m times a center of mass in x. Sum of the forces in y direction equals to m a center of mass in y. Sum of the forces in the x direction equals to, there is only one force in x direction, that's OX. Going to be OY minus mg. We'll put the numbers later on, but now we go to the acceleration. And we write down that acceleration of center of mass in x and y equals to acceleration of point O, which is 0, minus omega squared times O center of mass x, O center of mass y. Let's write down C is center. And plus alpha times minus O CY, OCX. The omega is 4. With OCX and OCY, we'll write down OCX is 0.4 sine 40. OCY is minus 0.4 cos 40. The alpha we found to be minus 5.11. And that's going to be, just a second. Yeah, this is correct. Now we go minus OCY, which is going to 0.4 cos 40. OCX is 0.4 sine 40. And now we're combining these things and we'll get the accelerations. On the x, we'll have somehow I don't like the numbers. Just a second, let me try it. Okay, it's going to be minus 5.68, and the other one will be 3.59. That's the acceleration, right? Now we go for the kill. OX equals to .24. Uh, okay. So far, so good. We have time for one more problem. Example 3. A spherical billiard ball is hit by force P. The radius of the ball is R. Find H, for which will not be slipping or any coefficient of friction, no matter how small. Of course, if the coefficient of friction is large, then the ball will not be slipping with the spinning, right? But we want to see for what should be the H. So the ball will be rotating and without slipping. Means we'll put at the end the coefficient of friction to be 0, and it will still be not slipping. O, C, A. Ball is of mass M. This is mg. This is n. And that's mu n. Again, we write the translational and the rotational thing, right? P minus mu n equals to the mass of the ball times acceleration of point O in x direction. O is the center. In vertical direction, n minus mg m a o the y direction. Well, acceleration of point O in y direction is obviously 0, right? So we'll go to the first equation, P minus mu mg equals to m times AOX. Now we'll go to velocity acceleration analysis. Here's a ball. From instant center of velocity c. It's instant center because this point is in contact with the ground and its velocity is 0. V naught equals to omega times r. That's at any moment in time. We'll take d dt of this equation. And we have a sub o, which is a sub ox, equals to d omega over dt times r, which is alpha times r. We will use this equation in a minute. We did the translational. We did this. Now we go over rotation. We'll use center of mass. So the moment's about center of mass of the ball. The center of mass is 0.0 equals to the I of the ball about center of mass times alpha. Let's mark the alpha because we keep writing alpha, but we never really showing what it is. We'll show it as if it is positive, even though it's not going to be positive. The moment at O will be P times H minus R. Moment of the ball about center of mass is 2/5 of mr squared times alpha. Now that is not a complete moment because there is also friction. But we'll say it has to be true for any friction. So friction ignored. Well, let's go back to this equation, which is going to be 1. This is 2, and this is 3. Back to 1. We'll set the friction equal to 0. E set friction equal to 0 equals to mass times AOX, and that's going to be alpha R. Let's just look at the sign. E is to the right. Minus alpha R because alpha is this way. Okay. So if we had alpha R, the center will be moving to the left. Is we'll put it in minus here. Now we equate these both p's, so we'll have minus m alpha R times H minus R equals to 2/5 of mr squared alpha. We can now cancel out the m's. Double check if my signs are correct. I don't think my signs are correct. Just a second. Let me just look at this one. This one should be okay. The P is moving this, so it's going to be minus. All right. Because the P is rotating clockwise. The alpha by default is counterclockwise. So now cancel the alpha. Cancel one of the R's. Put the H in the other side. H equals to R plus 2/5 of R. And there's going to be 7/5 of R. Sir. Yes. Say it again. The 2/5 is with a minus here. I move this thing here and move the H here.
I can see the negative.
Okay. Let's do one more problem. We'll start it. An 8-foot bar, 20 pounds. Is released from rest in position shown. Determine the initial angular acceleration. No friction. No frictions, there is no horizontal force. So write down that thing. That's one version of solving this problem. version 2, right? N minus mg, and the mg is 20 pounds, equals to 20 pounds over g, 32.2, times ACY. In the x direction, 0 equals to 20 over 32.2 times ACX. Therefore, ACX is 0. Moment about center of mass, it's going to be minus n times L over 2 times sine times horizontal distance sine of 30 degrees. Equals to mass moment of inertia, that's going to be ml squared. Sorry. It's W over G, L squared over 12 times alpha. Sir,
Is there any specific reason you want to see this just
say it again. Is there any specific reason why
minus? Have to take
gravity is 20? 20 is the weight. Okay. So let's count our beams. We have the unknown alpha. We have the unknown n. We have the unknown ACY. That's 3 equations, 2 unknowns. So we need to have one more. And one more will be the relative acceleration business, right? What we know is that vertical acceleration of the point of contact is 0. So write down that the acceleration of center of mass, which is this point, we know that ACX is 0, ACY is something, right? So we'll write down ACX, which is 0, ACY equals to acceleration of A, which is going to be AX 0. Now comes the term with minus omega squared, but they want us to find it initially. Initially means there was not enough time to develop an omega. Alpha is there, omega is not there. I'll write the term, but I'll cross it out so you'll know that it's there. And that's going to be the AC X ACY m plus alpha minus ACY ACX. So we introduced 2 more equations, but we introduced the one more unknown, which is ACY, right? Okay. Not ACY, what was it? AAX, right? So write down the first component. 0 equals to AAX minus alpha, and that's ACY is, that's going to be the 4 times cos 30. That's first equation. Second equation will be ACY equals to 0, and we have plus alpha times ACX, and that's going to be 4 sine 30. Let's just double check if the sign is correct. Yes. And we'll finish out the next time.